Hello, everyone, and welcome. I'm your host, Gregory Saxton, professor of accounting at the Schulich School of Business and co-director of Schulich's Center in Digital Financial Information, which is generously supported by CPA Ontario. We're excited to bring you today another webinar by Dr. Jerome Niyirora on hands-on guide to building your own GPT model. Jerome is an associate professor in the College of Health Sciences at SUNY Polytechnic Institute, SUNY Poly, where he teaches in the Health Information Management and Informatics programs and is the coordinator of the Health Informatics Graduate Program. He received his PhD in System Science from SUNY Binghamton in 2013 and also holds MS and degrees from SUNY Buffalo and SUNY IT. He does a lot of research on integrating system science, industrial engineering, and machine learning, and to optimize especially healthcare systems. And as you can tell, somebody is doing some lawn work outside. It's good timing. And Jerome has published in a lot of high-ranking journals. Before I pass it off to Jerome, I just want to say it reminds me of a quote by Douglas Rushkoff from the book Program or Be Programmed. And the quote is program or be programmed. A lot of accountants are interested in AI and maybe potentially worried about it. But either you're going to be somebody who tells the machines what to do, or the machines will tell you what to do. And so in that spirit, it's better to learn the types of stuff Jerome will be talking about today. So welcome, Jerome, and I will pass the stage off to you.
All right. Thank you, Greg. I appreciate your introduction. If you can make me share my screen, I can share my slides.
Okay, I think you should.
Yeah, I can share now. Yeah, great. Thank you very much again.
You're welcome.
It's a pleasure to be here talking about the machine learning and how you build it. So let me share my screen. All right, you should be able to see my screen. So again, I teach at SUNY Poly among the program and teaching health informatics and a new recent data science program where I get a chance to teach machine learning. And when I teach, obviously you can't talk about machine learning and AI without really talking about the natural language processing, which is essentially one of the areas where AI has excelled past several other areas. So what is the NLP problem? It's really the way you can teach machine to truly understand what's happening. And so as it turns out, this problem is still difficult, despite many advances in large language models such as GPTs and Geminis and the like. Solving this problem is difficult. And again, this is not from some code from other people. I tried to find one like this. I couldn't find one, but it's just essentially based on my own observations. So recently, there's a student that I advised. He was doing his thesis in data science, and he asked me, "Hey, can you be my advisor on this project?" I said, "Sure." He told me he wanted to work on a fever challenge problem. So the fever challenge problem is where someone makes a claim and they give you a set of Wikipedia pages and to verify whether the claim is supported or not. So at first I thought this is an easy problem. Just ask ChatGPT or just find a way to fine tune your claims to see if this works. To our surprise, that did not work. Obviously, because the ChatGPTs can generate the text, but they still struggle with the reasoning, truthfulness, and the context grounding. So those working in the area of machine learning, this is still a very interesting problem to work on. Of course, we had to celebrate the advances we've done, but the problem still remains. So you're going to find ambiguities and pragmatic and common sense sometimes missing whenever you talk to a program such as ChatGPT. And one of the reason is really language deeply tied to culture, to the context, cognition, the world knowledge. And to this point, at least the machine to understand this. Of course, the pragmatic perspective, it's not all is hopeless. I'm sure if you've got a chance to work with ChatGPT, you might have noticed how much is sped up time. It's made you find resources faster, and it made you restructure some sort of paragraph of sort, or just few things that 5 years ago was not possible. So we're making progress, which requires us to understand how this system work, so we don't end up, as that Saxton said, being the computer programming us. We want to be the ones programming them. So we know that with a lot of large language models now, they can really generate coherent and creative text. They seem to give a full sense of understanding, but there's really limitations. And the whole point of the talk is to try to demystify how these systems are. Hopefully, get a chance to maybe think twice whenever you get an answer from ChatGPT, but maybe even think about doing your own research in this area to advancing it forward. This field still has a lot of open areas of progress. And for this talk specifically, we'll be talking about Transformer. This is where the whole revolution started. We talk about ChatGPT, how we constructed, how you built it, and hopefully by the end of this, you should be comfortable in actually picking up this and go. I'm going to give you some great resources for those interested. Even if you're not a programmer, a book I'm going to recommend, it definitely walks you through slowly to how to do this. So the transformer is a phenomenon that probably wasn't known to anyone, maybe besides computer science and a few other fields that did the research in this area. I certainly personally was doing some work in those days was machine learning and natural language processing. That was the general term. AI was not very commonly used yet. And when this model came up, I didn't pay attention to it because there were so many papers being published about different areas of natural language processing that when this paper was published by Vaswani, too many people did not make too much of a difference. The surprising thing about the transformer, as we're going to talk a little bit later, it wasn't too much of a novel idea. It had been proposed actually a few years before this in a different context. Before the transformer architecture itself, there was something known as recurrent neural networks. Those are RNNs that were used for translations and all kinds of natural language processing. And so they proposed back in 2014 some sort of attention, because one of the problems those systems used to have is taking a long sequence of context of sentence and remembering several words back and put the context together when they were trying to, say, generate text or answer questions. So 2014, the researchers proposed, why don't we I call this almost a correlation analysis, just make a different words occur to one another within the sentence so the context kind of comes clear. That's really what the attention is. So they combine RNN plus the attention. But 3 years later, these other researchers realized you don't need RNN at all. It's the attention that you need. And that's really how the transformers were born. So this was the original structure of the transformer. Initially, it was built for translation. So that's why it was done. In fact, for a lot of the programs those days, it was much between how you translate, say, between English and French, between this language and that language. So it has an architecture that it's actually not what's being used now in at least the GPT models. So we don't really need this part only, the encoder. So the GPT uses the right side only, which is known as the decoder. So it looks complicated, makes no sense. We're going to go through each component by component and try to implement this through Colab to see how this works. So in this attention, this model, we have the attention mechanism. I talk a little bit about what this does. Essentially, just relates the context in a sentence to other words or even the paragraphs. As you know, when you, for example, you create ChatGPT, it sometimes refers to the conversation being having to be able to give you a coherent answer depending on the follow-up questions you have. Without having the ability to go back, it probably won't be making much of a sense of things it says. Again, the original model was it had this decoder and decoder, but the current applications of ChatGPT only use the decoder part of this. And we're going to see that it's essentially is a lot of neural networks stacked together. So it's what's known as feed forward. I'm going to demonstrate how you put this together. And for our focus for the talk, we're going to be talking about believe it or not, these GPT models are being applied to all kinds of data, including images and sound. As you know, if you give now ChatGPT an image, it can actually understand it. In most cases, describe what the image is. And same happens actually with sound. You know that a lot of these generative models can generate sounds that sound like a person and saying things they never said before, for example. So for us, we're going to focus on the text. The same ideas of how this works is the same. Once you understand how to work with the text data, it will be a lot easier to translate this into different other types of data. So just like in traditional natural language processing, for those who had a chance to work with machine learning, a little bit of Python before, every time you work with text, there had to be a way to make the machine understand what the text is. I mean, the text could be in English or German or Spanish. To the computer, it really does not matter. These are symbols that you have. You just have to find a way to tokenize them and give them a number. A number is just like an index of counting what those tokens are, from 1, 2, 3, 4, 5, 6 to whatever, as many unique characters and words you have in your text. So that's what we call tokenization. Split the text into words, characters. From there, turn those words into, again, almost like a database. You have an index. You give them IDs. So we're going to just be working with IDs, not actual text. And you could then convert this in something as embeddings, tensors. I can demonstrate to do this. And then once you start really getting into these transformers, you have to start thinking about how long can my system memorize the context when it's trying to generate text. The different length, obviously. The recent GPT models can memorize quite long sentences and paragraphs when they're trying to answer. There's something else we're going to talk about, which is padding and batching. These are just a little bit technical elements when you start training the models. But in terms of pre-processing, I'll call it, this is really important to understand why it's important. It's very straightforward to do. You can even do with a simple regular expression if you've used those in Python. I'm going to show how you can do that. So these steps are they really help to organize the text into something that the transformer models can digest and understand, and we can train it to generate the weights. And those weights are the one obviously we use for this purpose to generate text. So how does tokenization work? So this is, again, where you take your libraries or your corpus of training texts and just divide into unique words and characters. For example, if you have an example of a text, Apple's quarterly revenue rose 12%, year over year. That's like one. Let's say this could be your entire training set. In this case, it's just assume. So your first step is to create the tokens. So you're gonna essentially split the text by the characters or by space. So and then you end up with something like this: Apple, and then you have a little apostrophe S, query, revenue. You can see that even the numbers and these characters of percentage are separated. They're considered separate things because the compare here to learn what comes after what, right? You don't want this percentage put next to revenue, for example. It's the program is going to learn that the percentage comes after this number. And you also have these hyphens there. And you can, as you can see, this tokenization has some duplication. We really have not taken care of that part of it yet. But when you turn this into your IDs, we're gonna only keep unique words and tokens, and the integers we assign them is what we call token ID. Those are the ones we use for training the models. So in Python, we're gonna go to Python a little bit later. If you had to do this again, if you've definitely worked with Python or even other language, so this regular expression was one of initial way computer scientists were trying to understand the language, how to process this, and divide in a way that the computer can understand. So you might gonna find the regular expression in JavaScript, C's, and other programs. Certainly we do also have in Python. So once you just import R, regular expressions, and you find, this means you find each word or any following characters, or find any non-word characters. Once we find this, we split the text from there. And from there, you can sort it and create a dictionary of your library, of your vocabulary that you're going to use for training. Just a simple example. We're going to see much more advanced examples as we go to Python. And then you can obviously change this to tokens. We'll come to the code a little bit later. This is just a code. If you put this, run this into Python, you get the results. In the Google Colab that the Saxton shared with you, and there's a section where this code is going to be run. So once you have these tokens, you can now create a library. A library is you have to sort your characters and your words, so you keep only unique. So as you can see in this case here, we kept unique tokens. And these will be the token ID, like almost a library that you can search in to, or a dictionary you can search in to find what these tokens mean. Because if I say 3, what does 3 mean? 3 for us here means 12. 4 and 5 means Apple. So like if you had to convert this initial token into text IDs, you end up with something like this, right? So these numbers are the ones we feed into the program to learn what they are. To the computer, it doesn't matter what these numbers are associated to any other language, or even the language you never heard of, or even some symbols that you just made up. It's gonna learn how these token IDs relate to one another to generate a coherent looking text based on whatever you fed it. It doesn't mean understand what they are, but it can definitely learn those relationships there. So it is very critical that whenever you do work like this, you have to have a comprehensive vocabulary, right? Like if you try to build this system in English, you pretty much should touch on every single word of English. Maybe you can go to the local library and get yourself a dictionary of sort and look each single word, and then from there you can look at the characters and period, exclamation mark, and things like that. But I think in general, this the way the GPT were trained, it was on whatever was on the website, whatever was on Wikipedia. They digest everything. They generated unique comprehensive vocabularies before they could train it. So whenever you do something like this, though, it's possible that what if people make typos? Like when we all right, we can make typos, or people can come up with some new words that not really standard English that people did whenever they're speaking. How we take care of that one. So obviously when you do the regular expression, it won't help with that one. It's gonna consider whatever you don't have as just it's not there. But if it's not there, that will create an error in the system. So there's something known as bypass encoding. It's just was popularized by OpenAI when they first introduced GPT models. Essentially what it does, it replaces unknown words with tokens. Sometimes, like for example, unknown, it might use like this unknown. It might use some paddings. It might use end of text to indicate that maybe this is the end of a sentence. There's all different type of tokens that this system have developed to help us retokenize our text. WordPiece is another encoding system that's similar to BPE. It works just as good. So whenever we're going to tokenize our text for training today, we're going to use this system from GPT models. For example, to give an example, might happen if you try to say introduce this sentence as part of say your prompt in a GPT that never seen a word bracketed because it was never part of your initial dictionary. If you didn't take care of the unknown words, you have an error. But so essentially what happens in this case, this BPE encoding is going to replace whatever the word it hasn't seen by. This say unknown, and then it can give it say like an ID that you're going to find whenever you look at the token IDs. In this case, if you had to change Apple's revenue record, it would be 518, and then this 783 to indicate that this is an ID for unknown words. Again, in a GPT-2, which is actually what we're going to use today, when it was introduced in 2022, it had the size, really comprehensive size of 50,257. So this included English words and some new characters and some parts of words. Sometimes it breaks down the parts of words to help the model understand how different structures of sentences are made. So that's really what we're going to be using when we do the training. As of how you use the bypass encoding, it's very straightforward. There's several libraries that exist that have this algorithm, how it does it. So all you need to do is import, say in this case, you can use tick token. You can also obviously import this from something known as Hugging Face. It's open libraries of all kinds of open program software where it's a lot easier to find a lot of these open source programs. And ChatGPT-2 is there, so you can download that from there as well and just tokenize your text. So in this case, in tick token, we get the encoding that uses 50,257. And then once you use this to code the original sentence about Apple revenue rising, you get something that looks like this, right? So you have a different integers. It's just because it's used in this comprehensive vocabulary size that has this token that to replace those words. But once you revert these numbers back to the text, you recover the full text as we had it before, right? It's really easy to see how this kind of works. Once you have your tokens, you've took your initial text, you broke the tokens, you send the token the numbers, which is essentially the index you give them in a database. Now we need to do something with those tokens. We still have to find a way the system to learn the relationship between the tokens. So to do this, we do embeddings. So embeddings is you take a single word, the token, you represent it with a vector. So the length of the vector helps learn different relationship with context of, say, different paragraph, different words. So whenever, for example, you have these embeddings and you do like a correlation matrix between them, it gives you something similar to like just like a correlation matrix. It's something you do in statistics or even in traditional data analysis. In fact, that's what we do when we build the attention. We want to see how different pieces of the context windows relate to one another. Okay, so the embedding looks something like this, which is when you do training, these are usually random. Okay, you randomize this. But when you do fine tuning, okay, something I'm gonna briefly talk about later is you use your pre-existing trained embeddings. So these are trained as we train the model. So once you use the pre-trained ones, it saves you time because you just adjust whatever is needed for the system to understand the relationship within your own data set. You could use the pre-existing trained data, but use your own data set to adjust them. In coding again, this was surprisingly really easy. They understand the different pieces might be more challenging than the coding this itself. For example, if you had to do this, essentially we just call PyTorch. PyTorch is really being much more popular now whenever you build these open source programs. Is what's, at one point it was what's known as TensorFlow in Keras. But nowadays, every time if you talk to ChatGPT, can I help me write code for this? Most of the code now is being done through PyTorch. So Torch is something going to be using a lot here. So in this case, you call PyTorch. We tell PyTorch these are vocabulary size, these are input IDs. Output dimension, just manipulation of your matrices. In this case, you might consider this to be like your embedding size, just 5. But in general, this can be like 768 or even longer, depending on what program you use. So we give it a seed. A seed is usually something that you use in a lot of programs to ensure that you can reproduce your results, at least within your current session. And we just call embedding. Yeah, so that's all you do. You do it really to generate these embeddings yourself, even though you could really do it. You can start by randomize with some size of a vector and do it. But there's something better done to implement this, and this is just how you do it. And once you print this, for example, in this case, when you take Apple's revenue increase, you come up with these token IDs being represented by those embeddings. So there's, whenever you look at different references, people tend to use different words to mean sometimes same things, some different things. So one of them is that you might see like output dimension. In general, whenever you see this, people are talking about the embedding size. In a simple example, I just looked at our embedding size is 5. But in general, for example, when you look at GPT small, this is just a small version of GPT-2. It has the embedding size of 668. And a medium version of GPT uses 10,024. So it's just important to understand this. There's something also known as sequence length. This is more so like the context window. How much context, like the relationship between different input, can the model pay attention to? This is important because whenever you try to go outside of the sequence length or the context window, your model might start hallucinating because it's not connecting the context. So this is also important. And again, the key difference is just they do different things, even though people, you might find them using differently. The terminology might make a difference. So with this basic work we just done about tokenization and embeddings, we can actually start visualizing what's going to happen, right? So you start by raw text, you tokenize this into words or characters. You turn those words into token IDs, and those token IDs were turned into embeddings. So we're gonna put some mysterious function here, which is called for now called this GPT model. It does something with these tokens. It's usually read the attention, the relationship between them, and building the neural network there, and then it outputs this, right? It outputs these the tokens, And from there, there's a post-processing step that you do. Actually, it's essentially just do softmax, and then you predict the next word in the context. Again, the GPT models, as sometimes they sound fluent in what they're telling us, they can only generate one word at a time or character at a time, and that's essentially how they work. And it's still amazing to me how they can be coherent when they try to answer our questions. In any case, this is like a basic model based on what we've talked about so far. Something that originally RNN did not propose. That is when the researchers start working with these GPT models. They realize that if you don't keep track of where the position of the word is, the programs are having trouble sequencing the words in the right way. So the original all you need is attention paper suggested that you could do this using some sort of fixed position telling, kind of measure where each word is. Whenever I feel like in a batch of training, it can see which word comes before which one, right? So in the original paper, they wanted to use a sine and cosine function to capture this. It was not a trainable tensor. But later on, even the current GPT models, these are trained tensors. So you actually somewhat random and just train the position. What happens is that every word or token gets the same embeddings, but its input embedding is different depending on where it occurs in a sentence, say, or in whatever batch you're feeding it. So this is typically how you tend to have the final embedding before you start training the models. This was something that was added to, again, to give more context of position to the model. So when you do something like this, obviously what we need to do here for our basic model here is, again, go to token IDs. These were initial tokens. We add the position encoding again, which captures what each token is. And then once essentially just really adding them together, there's nothing else you do, just a plus. And then you have these input embeddings, and everything else is as before. And you can absolutely train this and keep going. In fact, something like this, if you have to train it, you get a pretty good results just based on this simple architecture itself. But we need to fill in a little bit details in there before we can get to that part. And that's actually the really main part of where the whole transformers contribute to the advances of natural language processing, is using these attention mechanisms. Can a model understand what the question is, put in the context of what it is in its training, and then generate something that kind of makes sense? So a single head mechanism was, again, originally introduced with RNN, but was refined to what we know now as the GPT models through these papers. So this was the original paper that had introduced the ideas of attention. Essentially what this is, you take your embeddings, think of them as matrices. You just do a dot product of them. And when you usually do a dot product, it's usually one part of the cosine similarities. And sometimes, if you want to really simplify this, think of this as the correlation matrix between different words in your input. That's what this @ sign does whenever you apply this in Python. So, and that gives you the attention weights. It's really nothing that more sophisticated than that. Typically, what we tend to do in training these AI models, we try to normalize every type of input we give them, and people realize it stabilizes your training. So in this case, you can just take your attention scores, which is, again, okay, this is just a dot practice, not correlation matrices, but we can easily normalize this so each row adds up to 1. And softmax is one of the functions that we use for this. Essentially, softmax, it's your exponential. You put in your vector here, and then you sum it up to exponential again with the same vector, and that's just how it ends up doing this. But you could find another way to normalize this. This does not have to be the only way. It's just the one that's commonly applied in training these GPT models. Again, this will be the code you use. Very simple again. Use the PyTorch library. And once you do this and print this, you just find this relationship between different tokens, apple to apple, as to quarterly revenue. And that way, the model is trying to pay attention to the words that give more correlated to the other, right? The only thing that's missing, obviously, you can see by this itself, is we're missing the positional element to this, which we put it in already. The other thing I'm going to talk about in a minute is this causal mask. The causal mask is like when you predict in the next word, I'm going to see in the last few slides, you don't want the system to know what the word is. When you're training it, you have to mask it, like give 0, and then you can try to predict to see if you got the right next word. If not, you have to try again. This through what's known as the back propagation methods, and you're gonna have to have a loss function to see the relationship between your input distribution and the expected distribution, and you want to minimize the difference between those two. This is where this causal mask coming in, and I'm gonna see this in the next few slides again. So this is essentially pretty much all the main pieces you need to build a GPT model. Okay, even if putting this together, it might even look a little bit easier. But before we do that, let me briefly take a few seconds to take a small detour to actually mention what it takes to build this. If you have not programmed yet, or very new to Python, a lot of the way the PyTorch is built is on top of functions and classes. If you want to build this, you just need to be a little bit comfortable in how you build them. So a function, just like a function in mathematics, it's the relationship between your input and output, between your x and y. In this case, if you want to build a function that relates a to b, in this case, you just want to do the sum. It's up by def. Then this is a name that you can give any name you want to. What's important is to tell the function what to do. And that in this case, this function do something like this. A class, they're very common in PyTorch. The good news, they're easy to understand what's happening. So they tend to come with two methods. You have a class. It's usually used in object programming. For those who've done programming other languages, they've seen this for sure. So the initial, or which is the initialization method, is where you essentially put your ingredients of all the things you're going to need in your forwarding method, which is where you combine different inputs, say, okay, to come up with something. In this case, when I create a linear neural network, again, usually neural networks, I'm gonna give you a picture in a minute. If when I relate them, you have like something like this, you relate to one another. So this is known as a linear layer in PyTorch or other programs. So if you want to have like a linear layer that starts with 2, then ends up with 1, like in this case, we connect this to 1. This will be linear to 1. Okay, you just want to cut what the linear structure looks like. This is pretty much a lot of the work you do when you're trying to build this. From there, so we talked about the embeddings, how you can do the embeddings. However, when the people did the embeddings and do the attention mechanism, they find a big limitation, right? You do this that product, but it's not necessarily giving everything you need in the context of information, representation of the content, or the value of the content itself. This is what essentially within the attention paper, they introduced these 3 learnable matrices. They're really the same as embeddings. They just look a little bit differently. You have something known as a query. And the WQ, again, this would be like nodes in the networks. You have something known as a key. This again is nothing more than just your nodes and networks, and the value. You multiply this together into what you end up with. That's known as the attention, right? So you take your input, your query. So that's like if you have, say, Apple's revenue rows, there'll be like your query. It's going to relate that to some of the metrics known as key, and then you normalize this and times that by your value. And out of this, you still get just one single attention matrix. And again, this is within context of nodes that comes out of this. So in attention papers, they found that this structure tend to help capture the context between different words a little bit better. It's just a little bit technicalities as a side note for those interested to know. Coding wise, this is again, it's not difficult. So in this case, you have like a self attention class. As we discussed before, you create these query keys and values as linear nodes within your neural network model. And then in the forward, you just do this dot products. And it's essentially the same thing as this. And you take these softmax, it's what's being done right here, and come up with your context vector. It's really easy to implement, especially once you start reading carefully through how these codes are built. Yeah, that's that. So one head is not good enough. So you probably want to have multiple heads. And people, I think originally in the GPT-2, they repeated this 12 times to really get the model to understand the context, right? I mean, it's not something that, this again, when people talk about this in this context, it sounds, obscure, but it's really all of this is connected nodes. So for example, when you have multiple attentions, you put them all together as a series of linear nodes, and then the output is these are the nodes again that learns the context from different heads that you concatenate it together, right? It still is a neural network that's being done to learn these learnable projection metrics. And once you have a single head attention, you can easily create a wrapper that reads this. You tend to use what's known as the module list. Essentially, just a for loop over my initial head. Just give me as many heads as I want. Again, the number of heads here, number of heads was 12 in the original GPT. We're going to be using that in a minute. Yeah, that will give you all the heads you need, and your model will have something like this. The only thing we add in here will be the attention. And then you have to program the transformer block. This is usually things general to training any neural networks. Like if you start reading on these topics, how do I train neural networks? We know how these attention mechanisms work already. It pretty much correlates different words to other words and contexts. There's also something known as normalization. Again, it helps, stabilizes the training. Activation function is every time you have two connection to a node, what's the relationship between the connection? Okay, so there's a function here that decides what this is. The function that's usually used is known as ReLU, linear units, but people have realized that this don't work as good, so they use this GELU, which is Gaussian. So ReLU looks like this. Means they're going to have a lot of dead neurons because so you only keep positive values. Something negative is 0, but the gel usually behaves something like this. Like, so it'll be smooth. So when you take a derivative, you don't end up with a lot of those dead neurons as you go through forward. Again, it'll be technicalities of what's being used, and that captures nonlinearities. And then you're going to have these feed forward layers, again, a bunch of linear nodes, and then you do this dropout to prevent overfitting. Okay, this is just a little bit technicalities of the remaining part of the transformer head that we need to put together. So once you do this, I think you have the whole model completely now. So you've tokenized everything, plus the position encoding. You normalize, you have the attention layers, dropouts, you have the fit for. This is really the main part of training, and how many layers you want in here. And then you're going to have this output. So what does this output look like after we've done through all of this? So the output looks something like this. It's just, again, another input of, this is usually like your embedding size that you started with. And this is the output size, which is your vocabulary size, right? So you're going to end up with some numbers in here, in your digits. And then you apply what's known as softmax. Again, is this E to the sum of This will be like your vector here that you have, okay? And then you maximize it. The biggest value is the next word. So how does the program know which is the next word? Because this arrangement relates to original encoding. So this will be 1, 2, 3, 4, 5, and maybe to 50,527 words, right? And each of these IDs, you can map it back to original word to find what the next word is. That's really how that's done. As you can see, training can be very expensive when you have a big library. But in any case, that's how that works. This is a little bit better view of what this is actually is. So the output, in your output layer, you have your initial embeddings, and then the output layer, it's your vocabularies that in GPT-2 goes to 50,527, and each one of these nodes represents a single token ID. And then from here, we can generate the text. When I was going to prepare these lectures, I could not find a better way to show this than showing the original reference I'm going to give in a minute to showing what's happening when you do this. So when you do the first iteration, this is like a sentence that says, hello, I'm a model ready to help. And then this is going to be your input. This is your next token that you predict. But that becomes also your input next time you try to predict the next word, right? So you kind of keep the context of what the prediction is. So now this is your input, and model will be your next output. And again, that becomes input again, then something ready. Because again, GPT produces one token at a time. That's just how it's able to somehow seemingly coherently reply to our messages whenever we ask it questions. It's all based on this basic masking and training using the technique that we've seen. This is another depiction. You can find these new slides, or if you had to convert those into numbers. We started with, obviously the text. We put those into IDs. We fed through this attention and feed forward the layers. We produce this output mechanism of this output layer with this not the same as a token. It's just a learned vector that represents what the output is. We apply the softmax. We maximize the biggest value. So you can see how expense we can get again to train this, and then you obtain a probability. The highest will be your next token. You map it back to the token and to the actual word, from token to actual word, and then you can make that as your next word, right? If it's not the correct one, you can try again through, the loss training function that you program within your GPT model, as I'm going to demonstrate in a minute. This would be like a function. Again, a lot of function classes you would use to generate the text and then put some explanation of what the different codes are doing. We're going to try to do this now in Python to see how this works. So this is the reference I use to put together most of my slides, and even the code itself I'm going to demonstrate in a minute. So if you're truly interested to understand how this you can build your own model from scratch, this is one of the greatest references I've seen. I tried to synthesize like 10 chapters into a few slides, but if each chapter usually walks through details, how you build the codes, how you what's the idea behind them, and so I recommend if you're interested in this topic. So with that, let's see if we can get to Python. So I'm going to go to Python. I think it should be able to see my screen. Let me stop sharing for a few minutes so I can go to Python, and I'm going to share again in a minute. In the meantime, as I'm changing to Colab, if you have any questions you have for me, you can suddenly start thinking of them, and we can entertain them in the next few minutes. First, let me upload the data that we're going to use. So I'm going to share my screen again. Let me know if you can see it. You should be able to see the screen. So this is the Colab notebook that you have. I organized into different sections so you can run through it. And I'm going to explain what's happening here. I have a bonus material known as retrieval augmented generation. I'll talk about why we need them in a minute after we've gone through the examples. So the first part of this code is essentially what I demonstrated in the slides. I'm going to just run the first line, but you can run the rest of them if you want. Again, what this is doing, it's importing the regular expression. In this case, we don't need the transformer tokenizer yet. And then it runs it, it just tokenizes it, just like we've seen. So you can run all of this. It's going to give you the same information as we had from the slides. And again, it's very easy to write this. So let's now worry about this preliminary code you've seen and start actually writing the code for the main GPT. This is going to be a model we built from scratch. We're going to train this based on the Tesla 10K filings. We're just going to get the risk analysis text and try to teach GPT how to read and understand, or generate something similar to what's being given in this analysis. So these reporting themselves were done back in, I think, during the COVID time. So the first thing I'm going to do is you import your libraries. Here we only need the very couple libraries: PyTorch, TikToken to do the embeddings, and then the Panda to just read the data. Okay, and then we run the data, the code for the text that we want. If you were interested to see what this looks like, text data. It just prints out what the text is, it gives the part of what the text is. This is what we're going to feed to our code to see what it does. As we've done before, your first step is to tokenize. You have to build some way of tokenizing your text. And this is done through these classes again, where you have input ID and target IDs, which means you shift by 1. If you can see here, it's like I plus 1. You shift by 1, so the next word is what you predict, and then on the return, the next word is going to be your input as well, just like what we demonstrated in the last couple of slides. So let's run this. This will be our data loader and tokenizer, both classes and function. Essentially what this function did, it took the tick token, this from GPT for embedding, and the data set class, which chunks the data into the input and target IDs. The next thing we've talked about this is our main layer. So we had to normalize the nodes, for better training. This is nothing more than just like creating a z-score, right? It's how you normalize to have a mean 0 and some variance. So we just run this. It's built as a class, so it's easier to apply within the context of the model. We have a multi-head attention. It's a little bit optimized than what I demonstrated in the notes. Essentially what it does, it has a little bit more layers to this and more heads, but the input is the same. You have the key, you have the values, you have the query, same matrices as before, but they're just nodes now within these linear layers. We have this forward structure that relates those keys, values, and queries together to context window at the end. At the end of this, you end up having the context vector that usually had the same size as your embeddings that you had. Let's run this. And now we talked about GLO, which is an activation function that relates, like I give a node, how do you put those inputs together, what comes out of it. It's used in this GLO. It's usually used as Gaussian, but people have come up with an easier way to apply this and train. So we actually code this in here. Under initial, there's nothing, and we just have the function here. We have the feed forward. This is where you essentially decide how many layers you want. So we have linear layers. In this case, we start by linear layers, the number of them, we times by 4, make it a little bit bigger, and then we come down again a little bit to make training more more capable of picking the nonlinearities correlations between different inputs. You can make this a little bit big if you want, but I think this was the original small size of GPT-2, so we keep that one. This is the transformer block. It puts everything together that we just had: the normalization, the attention, the dropouts, the shortcut, something known as ResNet, to train the model to learn a little bit faster. So we put that in there. And I think that's it. So we're gonna combine everything together into this class of GPT model, right? So we have this configuration that gives us what the vocabulary size is, what the context window is, embedding size, number of heads. These are all things that can change as you try to play around to see how this works. Let's run this. Now we're to train. So every time you train neural networks or any other machine learning, you tend to have a training and a validation set, so you can see how your validation set is doing. So the idea, you want to bring the validation error down. So it's just a small set you put on the side. So as you train on your main text, you can actually cheat a little bit to see how am I doing, given these are the texts I haven't seen. That's really what's happening here. In this case, we do a 90% split, 90% training, 10% validation. So we run this. This is just a training loop that calculates the losses and does the training. I wish I had more time to go through what each of these parts of the codes are doing, but for the sake of time, let's quickly run through this. And then go ahead and train it. Okay, this class organizes all the pieces together, and it took in our text, it tokenized it, and I gave it a start context of COVID-19 pandemic, and it started to learn like what comes next, something that might seem to be coherent. It's only 30 epochs and take 1 minute. If you can just hang in there quickly, we're almost there. You can see what this does. As going through this context, start context really doesn't matter. It's really meant for visuals only, for us to see what might be happening. So like how the model is learning. In general, you don't need to print this to see what it looks like. This was just for the presentation itself. Almost there. And as you can see, the more epochs usually how many loops you want to go around the code to fix it up. You can see that's getting better as it keeps going. For example, if I give a model Y as a prompt, let me see what it does. I say model Y face competition could result in the pass it may make. Someday, we only did 30 epochs. It's trying to predict the next word, but you can see from the results, it's kind of not as coherent as you want it. I also tried something like this, how is the planting buffalo? That's what was one of the things mentioned in the reports. When you do this, you say we are reported to have plans to enter the market election. You kind of start to answer based on the context you gave it. Obviously, this is not where train the model, but you can see the text being generated just by this simple model after 30 epochs and 1 minute seem to be making sense. So what people usually do, you want to upload your pre-trained model. In this case, if you had to upload your pre-trained GPT weights, this is the full model. It's a small one. And then you feed it into your own model. And then you just fine-tune it to your text. In this case, our fine-tuned text is 10K filings. That's what the code. You can actually generate something that makes a little bit sense. I'm not sure if Greg, I can have a couple more minutes. I'm almost done. So I can show what these results look like. So in this case, essentially what's going on as the model is going, we took the original weights from, again, using the same encoding as we've done before. We built this class to kind of relate this encoding to our own text. We did the same ratio of training and nothing different. And this is just to help her to do the calculate the losses. So after the training, now let's ask some questions. How did the COVID pandemic affect production, right? So this is original weights that we fine-tuned our own 10K filings, and then we can run this to see if something starts to make sense. Okay, so the temperature is something that tells the model whether it should be creative or be conservative in how they answer the questions. In this case, when I ask, how did COVID-19 pandemic affect production? I say we experience, we continue to face claims and regulatory, the kind of stuff gives a really coherent text. And then when you go to temperature of 1, it's in the first quarter of 2019, we produce a total of this. It starts to make not quite sense here. But then as you read, things start to make a little bit sense as you go. And when you get a chance, you can read through these responses a little bit later. So the lastly, quick briefly, is that in general, when you do this fine tuning, there's another way you can do this. You take the pre-trained model, but you build a library that's going to compare the text to the text. So what this means is that if you want to ask your model to give you evidence of if its responses, you should be able to generate this. And if you use this architecture known as RAG, you can easily implement this. And I just ran this. I don't know if I had time to explain what the code is doing. But after this ran, you can see what the model is here. At the end of this, the question here is, how did COVID pandemic affect sales? It gives you the responses and the evidence of what would that come from. This will be like the next step in the building models that can explain themselves. One, the trouble we tend to have when they talk to ChatGPT, can I trust what ChatGPT is telling me or not? Because if you don't know, you don't know, right? So this could be another way to force it to give you the evidence of what it's producing. And again, it's using this RAG architecture. And you have the code, you can certainly run through this and ask me, email me any questions you might have. Thanks again. This concludes my talk. My apologies, I won't be sure on the time to finish up everything I had prepared, but I'll be happy to entertain any questions you might have.
Hey, Jerome, thank you. I think we should probably let everyone head out for lunch. And since it is 1:04 now, I just want to say thank you again for joining. And this is, as you can tell, in order to talk with computers, a lot of Python is really good to know. And so that this is a little bit more advanced, but it's we do have other webinars that are easier. And this one, I hope you got a lot out of it conceptually. And the good thing with sharing the code is that you can go back and try it on your own time and learn it more conceptually. And so this, I think, is a great, really interesting entree into how you can customize your own GPT and LLMs and get some useful results. So thanks again for sharing. And join us on June 13th, where I will be doing a webinar on prompt engineering. And then we have another one 2 weeks after that on robotic process automation, which is another cutting edge tool. So thanks again, Jerome. And that was really interesting. And I learned a lot too, even though I'm a Pythonista as well. I thought that was really fascinating. So thank you everyone for joining us. And I hope you have a great weekend.
Thank you, Greg. Yeah, it's a pleasure. Thank you.
Yep.
Bye-bye.
Bye. Have a good day.